looks fine. So this is the block on kinematic control, okay? So this is a very important block. I'm sorry that we're getting at the end to this point, but this is natural in the progression of topics. So what is robot motion control? Why do we need to control and not just to plan motion for a robot? Well, the point is, as we already seen in the experiment, in the plots that are shown in the experiment of the KR5, that once we have planned in a very smart way, satisfying constraint, giving smoothness and so on, doing what the original task was asking, now we have to actually realize this motion task. Now we have two types of situation. When the task, it's a motion task, no? So indeed, something similar could be said in terms of forces, but this is not a topic that we have exploited in this course. We will see in the Robotics 2 classes much more about force and interaction control. But here in free motion, we either have to solve a regulation problem. So we don't care how we get to a final desired position, pose, or configuration in the joint space. So this is kind of assigning a constant reference. Or most of the time, we need to follow a trajectory, which is what we have planned in the Cartesian space, in the joint space, blah, blah, all these things. And in fact, we talk about tracking this trajectory, which means that we may also deviate from this trajectory, but we need to resume as soon as possible the originally planned motion. While in regulation, indeed, we have only given a constant final target, and the only request is that we get there as fast as possible, in a sense. So we don't care what we are doing in between. So if we have to do a pick and place operation, and the robot is in some home position, the first motion will be a regulation to the pick configuration, okay? Then we may follow a path with a given timing law, so a trajectory to the place pose, and then we move away and we just care to recover the home configuration. So depending on the task, you have regulation or trajectory tracking problem. Now, what is opposing the robot to do what we have planned? There are a number of motivations or reasons. First of all, there are external disturbances. No? So there could be accidental contact that push away the robot from the, let's say, the trajectory. There could be dynamic effect, friction, larger friction than we expected, so that the low-level loop will not be able to follow a relatively fast trajectory, so we have some error. This is what happens, for instance, in the KUKA KR5, together with the third motivation in this list. There's another issue that we may not start matched with the trajectory. So we have an initial error that should be brought to zero as fast as possible. Indeed, if you have some disturbance that intervene during motion, you will be moved away from the trajectory. And this is, if you restart time at this point, it's like having an initial error at the time that you have to bring back. So this should be continuously active at the initial time and during motion. And finally, you may have a discrete time implementation, and this is what happens in our case, in our experiment. And this will delay your commands, and you will keep also velocity constant for an interval which is too long. You should have updated this velocity at a faster rate, possibly continuously, which is impossible, in fact. And this will drift you away from the trajectory. This is why you need control, you need feedback, okay? So our control scheme will be based on two components. This is a general statement. So it will be a feedback part. So we measure where the robot is actually, which configuration the robot has. And then by feedback, we are able to stabilize the original trajectory, so bring the error to zero in an asymptotic way, or possibly also in an exponential way, so that we recover the error, or we bring the error to zero very fast. And this speed can be modified by the gains of our feedback controller. But on top of that, we use also a feed-forward term. So a command that is there, no matter if we have error or not. Actually, it's the command that will keep on track if everything is going well. And in fact, these are the commands that are being generated in the planning phase. So we can command the robot with several type of commands. If we are test directly to the motor currents, so we can impose torque, we have a torque-controlled robot. Unfortunately, this is very seldom the case. It's true only for some research robots, like the KUKA lightweight robots, not for a general industrial case, where instead we have a closed architecture, and we cannot enter into the heart of the controller. We can just modify reference in terms of kinematic terms. Okay, and this may be done at the position, velocity, or acceleration level. Usually, typically, the velocity level is the most used. Now, we will see what is the current stand, but the main thing that I would like to convey to you is that the feedback part is the one that brings the error to zero. And depending on in which space we are bringing the error to zero, the Cartesian or the joint space, we have different behavior, different problem, different realization issues, and so on. Okay. Now remember that can you hear me? Yeah. Okay. The command is always in the joint, at the joint level, because it's there where we have the motors. But how we close the feedback loop, this can be done in the joint space or in the Cartesian space, giving rise to two main kinematic control scheme of interest. This is the basics that we should keep, that you should keep with you even after the end of this Robotics 1 course. Okay. Indeed, as we said right at the beginning of our lecture, execution action is done at the joint level, but we evaluate performance at the task level, where the task is being defined. Okay, so why kinematic control of robots? Now, this is something that I already explained at the beginning of the course, and in fact, it was also one question of the remote midterm test. And now it's again explained. So we have seen that the robot is in fact a combination of electromechanical components, so motors, sensor, links, transmission, and so on. And the motors, now let's focus on electrical motors, produce torques at their output axis, and these torques are being transmitted to through reduction and transmission element to the links. So why can we talk about kinematic only if torque, which are a dynamic aspect, which involve inertias and other dynamic terms, are the source of motion? So we can consider kinematic command as control input to the system. Why is that? Because every robot is equipped with a low-level direct feedback control loop, which accepts reference in terms of kinematic quantities and generates the suitable torque using internal feedback as well, for instance, current feedback on the motors and velocity feedback or some approximation of it, and positional feedback in order to impose exactly the desired command. Okay, so this is the reason why, from the point of view of kinematic control, which is, let's say, 90% of the cases, we can assume that the low-level feedback control is doing its job perfectly, so this is the ideal case, and we only care about giving the right kinematic command as reference to this. Okay. Now, this is exactly what happened in a closed control architecture in industrial robot, and we will see now some, say, introspection into that. Okay. So now, this solves completely the problem? Yes and no, because if we look at the performance of this type of control, so relying on the low-level feedback control as if it was ideal and designing only a kinematic loop outside, and this kinematic loop is being designed by the end user, so by you on your PC or whatever, this works fine, provided that the motion that you would like to execute is not too demanding, which means that it's not too fast, and this is why we also introduced the time scaling, or it's not required not too large acceleration. So in terms of velocity and acceleration, in general, if you want to do things, I mean, if it's like moving an elephant by 1 meter in 1 millisecond, then of course you will need a huge amount of energy, even if you can plan such a motion. But then you're not guaranteed that you will execute in practice this motion, okay? So this is a general statement which I will try to illustrate through a simple example. So first of all, you can find this slide from actually from the second course of robotics. So I'm keeping, I'm putting them there, here just to illustrate this issue. So exactly with the KR5 robot, you can see on top a block diagram, which is what is inside the low-level control loops. So for each joint, we have a motor that generates a torque. This torque is being generated, let's say, by a motor that is driven by a current. So we have a desired current there, and we have a current analog loop that makes sure that the actual current circulating in the motor is equal to the desired one, and this will generate the torque. However, this reference for the inner current loop, which is typically analog, so it's not a digital control loop, comes from a velocity loop, which looks at the position of the joint, makes some numerical differentiation to get the current estimate of the velocity, compare this with a reference velocity or desired velocity QD dot, and make sure that this velocity is being executed, and the output of this is generating, in fact, the current for the inner loop. Again, this velocity loop may be digital or analog. Nowadays, most of the time is digital, but certainly is digital the outer loop, which again takes the current configuration, compares with the desired position joint by joint, and gives a command, which is the desired velocity for the inner velocity loop, in such a way that Q follows the desired D. Now, this QD, where is it coming from? Is it coming from a command from the end user? So we can command a reference velocity, for instance. If we do this, there will be internally a micro interpolation. So we update QR dot, let's say, every 12 milliseconds in our case, because this is the interface that the manufacturer provides to the generic user. And then internally, you generate an evolution of position from the current one to the next one, so you have a micro interpolation. Indeed, you may also, if you were able to generate position command at a faster rate and enter into the system, this micro interpolation would not be needed. Similarly, you could imagine, if you don't care about the actual position, which is almost never the case, you can enter directly with your QR dot as a Q desired dot as a reference for the velocity loop, but this is never the case. So this is a kind of playing around with the quantities going from position to velocity, velocity to position, and so on. But this is actually what you can do. Now, these 4 blocks inside are mostly our guess, because we cannot access to what is inside the manufacturer closed control architecture most of the time. We can expect that this is pretty much true, but we don't have the parameters inside. So the best we can do in this situation is just command this reference velocity, hoping that this velocity will go through. In this case, what you can access, in fact, all robots provide this information, is the current canonical encoders. So Q is available to you. And in this case, you have also available a measurement of the current circulating in the motors. Actually, for a strange reason, just the absolute value of the applied motor current for this KUKA robot. This is related to the fact that there's a PWM modulation inside the motor, and this signal is always positive because then it is mapped into a positive or negative actual velocity. So this is, I mean, it is used only for checking that you don't have too much large current going on in your system, and you can switch off the system in case of some malfunction. So you don't care about the actual positive or negative value, nor even of the actual value, just if it goes over some threshold. So indeed, you can, as we have seen in the language program, so if you're using the program language of KUKA, so the KRL language, you can specify joint velocities or Cartesian velocities, position, poses, and so on. So this is just a scheme which is intended when you're not using the actual programming language, but just commanding motion from outside. Indeed, you rely on other features that the control architecture has to protect the motion of the robot. So if there are some malfunction, if you're specifying something which is completely nonsense in the input, then there will be a protection and the robot will probably stop moving. And you can see on the right-hand side, typical motor profile, current motor profile of the first three joints over an interval of 20 seconds. So this is the closed control architecture that we have to deal with. And we can command only Q dot, but remember that what is actually moving the robot are torque at the level produced by the motors. So this is another scheme, and then we will resume the standard presentation. This is an old architecture, but it's an open controller. This is taken from the setup that they used to have in the Department of Computer Science and Control Engineering in Naples. So in the site of the first order of your textbook, Professor Siciliano, there were two Comau robots. We may have seen also one video of that. One was mounted actually on a rail, so it's a 7-axis robot. The other is a 6-axis robot. And these were Comau robots, and Comau developed a version of their controller that at that time it was the C3G 9000 controller, which is open. Which is open in the sense that they don't remove all their own controller, but allow the user through a serial port, an RS-232, to be interfaced with a special board, with a special board which is called B3, directly to the VME bus of the controller. So having the same authority of all the other elements in the controller, including the servo board that is controlling the axis of the robot. Now here, in fact, the serial port is between two external PC. One was devoted to processing camera information and giving reference to the control PC, which with board placed on its own bus, and the same board placed on the VMA bus of the C3G 9000 controller of the Comau robot, could even access to torque commands. So this is not only including vision and your own external controller, which could be done also on our KUKA robot, but is the presence of this board that connects directly, and of course, real-time operative system. So this is real-time Linux running on the PC, could enter into the core of the controller. So substitute what the original controller was doing at the level of current of torques. Okay, but this is not the case in our setting. So let me explain what do we mean by ideal behavior of the low-level loop. And I will do this by a very simple example, the simplest example that I can think of, which is moving a single mass, so a single degree of freedom, subject to a force. So we have a mass m, we have the Newton law describing this dynamics. Now, for the first time, we are introducing the concept of mass. We can represent this dynamics with this block diagram, which is very similar to what you would do in Simulink if you're using this graphic interface. So you start from the end of this chain, you have a position x. Okay, there's a question that I will answer later on at the end of the lecture. You move one step, differential step before, so you go in the reverse direction of the integration, so you have the derivative x dot, and you have another integrator, so you have at the input an acceleration, and this acceleration is nothing else than 1 over m, the applied force. Now, if you would be able to apply directly force with your motor, then you can command the motion of this mass in the way you wish, following the trajectory, rest-to-rest motion, whatever, okay? But in fact, you cannot access directly to F. What you can do, you can measure x dot, or better said, the low-level control, low-level feedback, can measure x dot and compare this with your command u. This is your reference velocity, the QR dot that I mentioned in the other slide, okay? And now suppose that based on the difference between what you command as reference velocity and what is the actual velocity of this mass, x dot, you have an error, and you react to this error with a gain k. Now everything is scalar here. This is really the most simple example that I can think of, and you generate the command force in feedback, in fact, by multiplying by k the difference between the reference velocity and the actual velocity. Now, what happens if you are allowed to bring k to a very large value? Everything works in continuous time here in this simple example. Then, by bringing k to infinity, you will see that the error will be brought to 0 very fast and very soon and very permanently, so that you can assume that the actual output of this brown block is ideally 1. So x dot is exactly what you're commanding. Okay? And this is true if you have very large gains and if you can tolerate very large gains. Of course, this in practice is not true because you have saturation, so you cannot bring k to infinity. But in principle, if this is true, the whole loop between u and x dot can be eliminated, can be substituted by a 1, if you wish. So what remains is just the integration of x dot into x, but x dot is exactly equal to u. So your model of this mechanical second-order system is in fact a first-order model where you can command u, and these u are going to be integrated into the position x, okay? So this would be what you do if the low-level loop Brown in the robot, so the direct controller of the manufacturer, is very good, so that you can neglect this dynamics and replace the robot just by a single integrator between your command and the actual position. Now, in practice, this is valid for a finite value of k. So in terms of bandwidth of signals that you can reproduce, there's a limitation, and this bandwidth is nothing else than the ratio between k and m, which means that the larger k, the more frequency of the signal u that you're commanding. You can command the sinusoid, but you can command also a non-sinusoidal trajectory, which can be decomposed in its Fourier contribution. So many sinusoidal with different energies at the continuum of frequencies. But you have a bandwidth, so up to k over m, you can reproduce. Beyond that, you cannot reproduce these components. So you have a deformation of your original signal. So as I said, if you increase k, this bandwidth is being enlarged, but even for the same k, the smaller the mass, the larger is the bandwidth, which means that with the same k, you're controlling better a small mass than a large mass. Better in the sense that you have a larger bandwidth to work with. Okay, so if you are familiar with both diagram, this is a linear system, so you can do the Laplace transform, you can replace S by j omega, and you have a frequency response, so both plots in magnitude and in phase. Actually, what you care is magnitude, and this is just the transfer function between the commanded reference velocity and the actual velocity, not neglecting the loop with the gain k. And you can see if you, what matters is just the ratio between k and m. So if this ratio is 0.1, then you have the green plots, and you can see that you have 0 decibel from the zero frequency, so from the continuous signal up to some frequency, and 0 decibel means a ratio of 1, so you're reproducing exactly whatever frequency you have from the continuous until 10 to the minus 3, 10 to the minus 2, and 10 to the minus 1, you have an attenuation of 3 decibel, which is where you start losing reproduction capability of those frequency components, because you have an attenuation of 70%, okay, of what you had before. The phase plot are not really interesting. Indeed, if you increase this ratio, either because you have a smaller mass or because you're increasing the gain k, you bring it to 1, 10, 100, and you can see that accordingly the bandwidth is being enlarged. So there's a larger frequency interval that are being perfectly reproduced. Now, if we choose, for instance, a bandwidth of 10, so the ratio k over m is 10, and now we send the velocity reference, which is sinusoidal, just for simplicity. And if this sinusoid is at 2 radians per second, then the actual velocity, so what you get as a result of this mass, will practically be the same. There's a small attenuation, but you have a signal which has the same frequency of the input reference velocity, so 2 radians per second, and practically is being reproduced because you're well within the bandwidth. Indeed, if you now put in input a faster oscillating sinusoid at 20 radians, which is 2 times larger than the bandwidth, you see that apart from some transient, at steady state you have exactly the same frequency of the signal, so at 20 radians per second, but an attenuation of about 7.5 decibel. So you have a peak-to-peak of 0.8 rather than of 2. So you're not reproducing this signal because you're beyond. So you can say that your local loop works well within a bandwidth, so it can reproduce whatever command immediately you're giving if this command has a frequency content up to the bandwidth. But as soon as you have components outside or fully outside, this is no longer true. So your ideality is lost. I hope that this simple example was clear to everybody. Now I will make, as a matter of introduction to the real world, I would say, a more detailed example, still a single degree of freedom, but where masses, inertia, gravity, and nonlinear dynamics enters into play. And this example is an example of a pendulum, an actuated pendulum, still a very simple example, I must say. But in this case, if you consider only the kinematics, this is a rotating link, the joint axis is at the base of the pendulum. So we have a single variable q, which describes the position, the angular position of this link. This is the kinematics in sense, with respect to some x0 axis, which is taken as the vertical, because this is the direction along which gravity acts, and this is a common choice. We have a motor. The motor is producing a torque at the joint level. There's an inertia of the motor, which is labeled here as EM. The link itself has an inertia, and typically there's a center of mass. Suppose that this is a uniformly distributed mass link. So its center of mass, or barycenter, is at more or less the midpoint. But in any case, you can always locate this center of mass at the distance d from the rotating joint axis. At the center of mass, you apply the gravity force, which is the small m mass of the link times the acceleration 9.81 meter per second, always pointing downwards. So this link has an inertia, and when it rotates around the center of mass, this inertia is IL, but in fact, due to the parallel axis theorem, we are not rotating around this axis, we are rotating around an axis passing at the base of the link. So we have to add to this minimum inertia of the link a quantity which is the mass of the link itself times the square of the distance. So this is the third term, md squared. So if we do the balance of torques, like the Newton equation F equal ma for linear quantity, there's an equivalent relation with momentum and angular acceleration and inertia. So the total inertia that the motor torque should accelerate is the sum of the inertia of the motor and of the inertia of the link rotating around its base. So it's Im plus IL plus md squared. And this is multiplied by q double dot. And this is equal to the torque that I'm applying. But I have to subtract to this torque, or bring to the left-hand side, so with a plus sign, the force of the gravity force. Because even if I'm not applying torque, under the action of gravity, this pendulum will fall down, will oscillate, and then will probably stop. There's no friction model here, but there's always some friction in the devices. So after a while, the oscillation will vanish. And if you look carefully at the sign, you see that the force is pushing clockwise down. The gravity force is pushing clockwise down this link, while the positive torque is counterclockwise. So if you bring this term to the left-hand side, this will oppose the torque. Okay, so you can write the model in this way. And here I put some numbers, some physical numbers that represent what happens in this case. Now we assume, let's see how ideal can be a low-level feedback loop. Now I have to design a feedback control loop, and I made a choice. We don't have time to discuss this choice, but it's a proportional integral action, so a PI controller on the velocity error, proportional to the velocity error and to the integral of the velocity error, which is nothing else than the position error. And then I have also a feed forward, since I'm working at the velocity level, the feed forward. So I'm reacting to a velocity error, so generating an acceleration in reaction to the velocity and position error. If this error is completely zero, then I need to send an acceleration feed forward. And this acceleration feed forward will be based on an approximation of this dynamic model. Well, it's nothing that we have to care about, but I would suggest, once we have done robotics 2 and control using dynamics, you can return to this example and understand all the subtleties of these choices. So we will have this low-level feedback loop, and we will have a kinematic control loop outside, so what we can really impose. And in the kinematic control loop, we will use a proportional action like we did for the simple mass, but now on the position error, because we want to track a motion of the position of this link. We just don't want to control simply the velocity, but actually we want to bring this pendulum, up or horizontal, move it sinusoidally, whatever. And we also have a feed forward in terms of the velocity reference at the joint level. And here the Cartesian is just a scaled factor of the joint space. We have only 1 degree of freedom. Okay, so this will be the setup, and we will evaluate the tracking performance of our scheme while we are demanding faster and faster motion. So we are increasing the dynamics of desired motion. So essentially we're requesting more acceleration, and we will see what happens. So in order to test this, I set up a Simulink scheme, so a block diagram. I suggest you to make acquaintance with this object. For those of you who are following the control engineering master, this is, I would say, mandatory. For the rest of you, it's a very elegant, very simple tool to use when you want to simulate the system, both kinematically or dynamically, whatever system you have at hand, a mobile robot, manipulator, but also a satellite, also the dynamics, the skidding dynamics of a car, whatever, you can simulate it in Simulink. So the three large blocks, which are exploded then, are the violet one on the left is the generator of the cubic position profile. So we are using the cubic position profile with faster and faster velocity, probably. The block on the red with the green one is the real behavior. And you can recognize there the low-level loop inside the block, which is masked, which received a reference in terms of velocity, QP means Q dot reference, and it's exiting with an actual velocity. This actual velocity is being integrated and becomes a position. This position is used by the lower level controller, but also measured and brought back and compared to a reference position, which is what coming beyond the integrator of the trajectory generator. So we have a reference velocity and a reference position there. The reference velocity becomes a feed forward. The comparison between the reference position and the actual real position becomes an error, through which we respond with a gain, the proportional gain of the feedback part. So we have a controller which generates the reference velocity for the low-level loop with a feed forward of velocity and a term which is proportional to the position error, which is the feedback part. Now, inside the green block, there is the low-level controller. Now, we don't know exactly what it is. So if we assume that this is ideal, so that the reference velocity that we are commanding will also be the actual velocity of the robot, then this green block inside will just vanish. And in fact, the ideal behavior is replicated in this simulation below, so that we can compare what's we believe it would happen if everything is real with what is really happening by looking at the complete dynamics. Now, if we expand this block, and I will just skip, not comment too much this block, we see that on the left side, we have the torque produced by the motor and the dynamics with the total inertia of the motor plus link and the gravity effect. And then we generate an acceleration. This acceleration becomes a velocity after one integration, which is represented by the factor 1 over s in the Laplace domain. And this is what we exit from the system. It will be integrated and generate a position. The torque is being produced by our low-level control loop. We model the actuators simply as a saturation, so that we cannot generate more than 100 Newton meters. So this is a saturation placed there. And the low-level control loop is of approximate acceleration feed forward plus P. I'm not commenting this. I'm just noticing that it takes the reference velocity as input and generates the torque. And this is what we cannot open from our control architecture. Okay, so now let's see the results, and then we stop this part, and I will answer to the questions that are online. So we would like to make this motion a rest-to-rest motion, so the pendulum is standing still downward, and we would like to bring it to 90 degrees in the horizontal position, okay, in a certain amount of time, and using a cubic profile for motion and some gains and whatever. So this is what we will do in this position tracking and the position error. So if we do the motion in 1 second, you can see that we will move from 0 to 90 degree. This is the actual motion. We are using k equal 50 and 1 second. So we don't really understand the difference between the dashed line, which is the reference, and the actual line, which is the blue continuous line. So I've traced the position error below, and you can see that this error is about 0.2 degrees, which is acceptable in this case, okay? Now, if we speed up, so we half the total time, so remember, which means that the velocity are doubled in this motion. The acceleration becomes 4 times the original acceleration. Still, you may look carefully, you can recognize the dashed red line below, but still the error remains very small. In fact, below you don't see any difference. Now, if you half again the time, so you have 1/4 of the original time, which means that the velocities in this motion have become 4 times as large as before at every instant multiplied by a factor of 4, and acceleration by a factor of 4 squared, so by a factor of 16. Now you can see the difference between the planned cubic, which is the dashed red line, and the actual motion. And in fact, this is bad tracking because you have a maximum error of 5.5 degree, which is a huge error, I would say. You see that nothing has changed, same gains, only requesting a more demanding motion from the dynamics point of view, the low-level controller starts failing. So its ideality is gone, okay? And in fact, if we now look at the high-level command and the low-level torque command that are actually being generated, in the 1 second motion case, you see that the velocity command, which includes a feedback error term, and which is practically not acting because the error is very small, and an approximate feed forward, has this profile, which looks like the velocity profile of a cubic motion, okay? And the torque inside, which is something that now we are doing a simulation, so we have access to any signal in the simulation. You can see that it's a kind of a negative positive variation because it has to contrast gravity, getting against gravity, and then keeping at a steady state position, okay? Now, the first part, in fact, is dominated by the gravity, which is changing as a sinusoid, while at steady state, after 1 second, we keep a torque with the controller because this is what sustained the link in the horizontal position. The torque cannot go to 0, otherwise the link would fall. And this non-zero value with 0 error of position is provided by the integral term in our low-level controller, for those of you who are more familiar with control techniques. If we speed up motion, as we have seen, you see that the kinematic command, the velocity command that we're generating, so the QR dot, is almost the same as before, while all of a sudden, the low-level torque profile changes behavior, and the sinusoidal behavior, according to contrasting gravity, of linear behavior, which is much more similar to the acceleration profile of the cubic motion. You see that acceleration becomes dominant. And if you speed up further, you see that there's a complete deformation. You will have error. So the high-level velocity command, it's not only the feed-forward term, it's also trying to react to the error, because without this reaction, we would completely go off of the original trajectory. The low-level torque now is completely different because saturation has burst in. Not because we have increased the gain. The gain is always 50, but the error has become so large that multiplied by 50 brings the motor in saturation, and then we have this type of disastrous behavior. So not really disaster, but so large error that are not acceptable in a robotic application, okay? So I think that this is an extra slide that just replicate the error in the 3 cases, the real error. Of course, if we consider the ideal model, in no case we would have seen error, because we assume that the low-level loop, so is the lower block of the simulation, is doing things as if everything remains idle, no matter how fast you're doing this motion, okay? And the error is always 0 because we start with 0 error in position, so we are matched to the desired trajectory. No error will arise, no sensitive error will, sensible error will arise. So the position error remains 0 at the whole time. In the real case, in fact, is completely different. And I think that by that, yes, I will stop here, and we will resume with the last part, with designing kinematic control in the Cartesian or in the joint space in the lecture of Friday. So there's any question on this part, on this last part? If not, I will answer now to a question that was raised on the scaling. So Francesco Argenziano is asking, can we check analytically if we are violating the bounds, or we can discover this only by plotting this law? No, of course you don't have to plot anything, but in order to check if you're violating, you have to know the velocity at every instant. You have to know, of course, the bounds, and then you can compute while you're getting data from your system, so from your robot, you're computing if you're violating or not, and if you're violating, you're increasing the K of violation until you have completed the motion, and only then you can check what is the most violating instant and value of K, and then you scale things. So you can do this without plotting anything, but in practice, you have to collect the data of all the motion before understanding which is the worst instant of violation, or if there's no violation at all. Okay, so thanks for listening. And as I said, those who have made remote meter terms, by the end of the day will receive their grade. And we will discuss, we will have time on Friday for completing this, for discussing the remote midterm test, and also, or in alternative, if you wish, to discuss any question that you may have. So prepare your question, because this will be probably the last occasion before Christmas, and then there will be vacation. I will be reachable at any time, but only by mail, and so it's the right moment to have a direct interaction on whatever doubts or question you have on what we have covered. Okay, bye-bye.